Hello, my name is now Asio Nicole, and I'm going to be taking you Group 41's project for like the first 5 slides. So our project was reinforced quantum future learning for indoor air quality monitoring with ensemble knowledge distillation, indoor air quality monitoring for indoor air quality monitoring. So basically, indoor air quality means that the higher the concentration of pollutants within an environment, the poorer the air quality. So the increasing prevalence of indoor air pollution due to poor ventilation, emissions from household products, and external pollutants necessitates a robust indoor air quality monitoring system. And our project's objectives is to develop a real-time indoor air quality monitoring system that incorporates predictive capabilities. By this, I mean, since most of these models need improving, and that means the more data you have, the more accurate your model is. With our system, we could partner with other innovators to give them a data set from our app that collectively with embedded IoT sensors gets more data on the concentration of pollutants in the environment to improve models in like the future. Then also will provide actionable insights for interventions and also enhance public health outcomes. Our solution overview. Let me start by asking you a question. How much does the average Ugandan spend on health regarding respiratory diseases? I could bet that at least at least all of you know one person with asthma or like two people with asthma. And why our app matters is because a lot of these respiratory diseases are caused by the concentration of pollutants within an environment, which our app will help monitor these concentrations and send you notifications on how to control or like survive that environment. What I mean is our app will be able to notify you whether there is poor ventilation in the room. Maybe you need to open windows. Or as an asthma patient, maybe you need to have your inhaler close by because you find yourself spending consultation fee 200,000, medication 300,000. An inhaler itself could be like 300,000. With our app at just a subscription fee of 150,000, you could be told on how to work around the concentration pollutants within your environment. And I feel like with our app, which we calculated, it was estimated that you would save over 800,000 and be able to still keep your health in check. Yes. The model we used was a temporal convolutional network model that processes numerical time series data from indoor sensors to predict air quality levels and classify them into categories. And this came out as our most accurate models because we are trained 10 models. And the combination of predictive accuracy, computational efficiency, and real-time processing provides a novel, practical solution for mitigating health risks associated with indoor air pollution. Then the data we used the GAMS indoor data set, we used, which was public and it was sourced from GitHub and indoor sensor networks. It contains data collected from various sensors monitoring air quality and environmental conditions within a specific location and environment. The data is organized with the following features: carbon dioxide, VOC, PM 2.5, PM 10, humidity and temperature. And it had over 13,000 inputs, which was less than what we needed to make our model more accurate. But with our current model, we believe that we can create more data sets for future innovations to help mitigate health risks regarding respiratory diseases. Thank you. I'd like for you to be taken through the next part by my colleague. Have a nice day.
Hello everyone, I'm Irene and I'll be taking you through the models and techniques that we used in our project in machine learning. And we had our models basing on their suitability for processing a numerical time series dataset, capturing sequential dependencies as well as addressing the challenges of real-time indoor air quality monitoring. And our models included the graph attention networks, the temporal convolution networks, the transformers, and many more others. Then in our architecture, we started by collecting of data, and here we got it from our dataset, which was the GAMS indoor dataset, and then we processed the data, did the exploratory data analysis by cleaning the data, doing the statistical analysis, making visualizations for our data, as well as feature selection. We were also able to develop our models through training them, and we evaluated them using the hyperparameter tuning, which included the learning rate and the training time, and we're also able to select our models basing on their accuracy. And TCN, which is the temporal convolution network, emerged as our best performing model with an accuracy of 93%, and the self-organizing maps emerged as our worst performing models with an accuracy of 88%. Then we implemented our models using languages like Python, libraries, for example TensorFlow, Pandas, and many others, and also used Google Colab as our major platform during this work. Yeah.
within the environment. What are the relevant what are the relevant features? Is it going to be relevant to the environment that we're trying to figure it out? Is it going to any problem within the environment? Yes. How are we going to see this? Health implications. If we are to look at the health implications, we know that the poor air quality, indoor air quality, can lead to the respiratory systems and cardiovascular diseases, even lung cancer. But where Uganda healthcare resources are very limited, preventing air pollution related illness is essential. How is it going to impact? Whereby if these resources are very limited, that means that our system will help in improving on the health, whereby no more Ugandans or their health are being affected. That means that the resources which are limited will always be enough for those maybe who have refused to undergo the procedures of our by the way, we also have the economic benefits. How are the economic benefits? How is it going to benefit economic? How is it going to benefit it? Through reducing the costs. How? If you are to introduce remember, person has been suffering diseases, upper respiratory diseases, buying inhalers, suffering from asthma every 3 months. So this app of ours, this system of ours will enable them to limit on their way of course via the respiratory health, environmental sustainability. If we are to improve, like especially indoors, if there was, let me say that majority have been using gases, like this gas, like the gas that is used for cooking. Remember, it produces a volatile organic compound, which is the methane. If it has been left open, some people will inhale it and lead to, like, if at all our project or our system is there, it will try to sustain the environment through detecting and monitoring these air pollutants. Our project really aligns with the following SDGs: good health, well-being, sustainable cities and communities, climate actions. Yeah. The improved health, now these are the really good. It will improve on the public health. It will increase the awareness of how to monitor quality. It will inform the policy decision and economic growth. If we go to the next slide, we shall have the intellect here. So far, how are we protecting the system? Protecting the system, let me say, protection type, we have the patent, have the copyright, we have the trademark, and the trade secret. What majorly covers the novel algorithm, make processes, especially the patent and the innovation. So we shall be protecting our model, which is unique, which is used from not used by any other person, maybe. Then the copyright, it's the software code and the UI design and the documentation as well. Our research paper, like our concept paper, our the trade so we shall also treat the secretary like the protection within. I'll be showing you. I'll be taking you through how the how data and the crowdsourcing and it also have a strong brand name and a user base. What are our deals in indoor air quality? The air quality and how to monitor the air the home. And advantage of applications where people will be able to interact with the users. From the
Hello everyone, my name is Nantongo Jocelyn Madrin, and I will continue from where the previous presenter stopped. I'm going to take you through our lessons learned and the technical challenges, our future work, and the conclusion. So this is our team contributions. When we continue, when we go to our lessons learned and challenges, some of the technical challenges we faced, one was we faced a challenge of getting a data set. Since we are testing and training models to monitor indoor air quality monitoring, it was hard to get the data set of indoor air quality in Uganda. So we had to discover some data set that we could use from India to train our models, as we've been seeing that we sourced our data set from GitHub. And another technical challenge we faced was fine-tuning machine learning models, that is quantum machine learning, for accurate predictions of indoor air quality. So balancing model complexity and performance was tricky. There was overfitting. Overfitting could reduce generalization. Also, the availability of high-quality data for training models was sometimes a limitation, requiring data cleaning and processing efforts. And the lessons we learned more about data cleaning, training our model, evaluating our model, choosing the best model, and how we chose it is by looking at these metrics such as the MAE, the accuracy, the learning rate, the training rate, the F1 score, among others. We also learned that teamwork is the backbone of everything. Through teamwork, everything is possible. Work moves on well, and it's good to work in a team. When we go on to our future work, what we intend to do or to add on, we intend to look at multi-sensor fusion, and these are techniques of integrating the various gas sensors such as carbon dioxide, carbon monoxide, PM2.5, to capture a broader range of the pollutants, so that we make sure that we are getting correct data. Yes, so that expanding of the indoor air quality research will include diverse indoor air quality environments such as the hospitals, the offices, and this is crucial as many studies have focused mainly on residential and educational settings, leaving gaps in knowledge of other areas with significant air quality concerns. We shall also look at real-time indoor air quality monitoring with smart building technologies, and this can enable automated adjustments to ventilation, HVAC systems, and humidity control, reducing pollution and enabling occupant health. And finally, we shall look at collaboration between the policymakers, the researchers, and industry stakeholders. Since this is needed to translate scientific findings into effective regulations and public health initiatives. We shall also look at expanding the datasets into getting bigger datasets and generalization, so that we can improve on model generalization and also improve on getting correct data. That we shall also look at creating our own datasets. We shall also look at cloud connectivity, that is storing and analyzing data on the cloud. Remember, as we are expanding, we shall need more space, shall need more resources, so that's where we shall look at working on the cloud, storing our information and data on the cloud. And in conclusion, this study critically reviewed advancements in indoor air quality monitoring and source identification, focusing on both traditional and emerging technologies. So the impact of our approach, whereby, as the previous presenters have been talking about, we want to call it air safe. It could lead to better public health outcomes, particularly in environments like schools, hospitals, and public spaces. So our final message is to truly improve indoor air quality and public health. Future research must focus on developing affordable, scalable monitoring systems that combine local sensors with advanced data analytics, ensuring that every community can access and act upon critical and air quality information. Thank you very much. We remain Group 41. Thank you.